Good afternoon, everyone, and thanks for joining us for our presentation today. It looks like we're going to have an intimate crowd, so feel free to, as we move through the material at the end, we'd be happy to address any questions that come up. We have a lot of material to cover, and hopefully you'll find it interesting. My name's Philip Father, and I'm with Scepter, and I have two colleagues today presenting with me, Chance Thomas of AWS and Emily Reedy from ExxonMobil. And we're going to run you through a bunch of material on monitoring the atmosphere and how we put together some compelling platforms to do that. And we're broken up into a couple of different portions. I'll run you through Scepter, and we're going to have Chance walk you through how in-depth we've built the platform and what we've accomplished there in collaboration. And then Emily and ExxonMobil were kind enough to join us because they've been instrumental as a customer off the platform and helping us develop methane detection use cases. So here we go. We monitor the atmosphere, and the three of us today would like to take the opportunity to share with you advances in big data, data analytics, cloud computing, and the new space economy, because those areas have fostered the ability to monitor the atmosphere and monitor the atmosphere on a global and real-time basis. And what we're really doing then in that context is we're making the invisible visible. But why would you want to make the invisible visible? Well, there's a lot of elementals and gases and particulate matter from air pollution that if we were able to detect and quantify them, they're of interest to commercial markets and to governments. So that's why we've set forth to do this. Maybe I can give you a few examples and to give you a little bit of context. So why don't we pick nitrogen dioxide? Why would you want to see nitrogen dioxide? Well, do you know that NO2 and air pollution in general have been linked to depression? Heavily linked to depression, empirically, lots of research, and that as a result of that, NO2 is a big driver in that air pollution mix. So I think it's about 21 million people suffer from depression annually. That's probably 8 to 9% of our population. So people here today, if you knew about NO2, and maybe that's the trigger to your depression. And instead of running to the medicine cabinet and getting your meds, maybe it's actually a result of the air that you breathe. And big pharma and industries like insurance are very interested in this data set. Let's pick another. Why don't we take particulate matter, PM 2.5, and ground level ozone? What's a use case there? Well, collectively, these two constituents have been found to substantially inhibit agricultural production and crop health. They inhibit photosynthesis and do other negative things. So like an estimate of that would be 1% increase over a norm for either the gas or particulate matter. That can trigger $5 billion in global economic harm as it relates to agricultural production, just a 1% increase. All right, so that's an example of why we would want to know that. So big pharma would like to know that. Insurance would like to know that as well. And let's take another. Why don't we just go to methane and carbon dioxide, because we're here today to talk to you a little bit more about methane, but I wanted to give you context. So we all know about methane and global warming and how it's contributing to problems here on Earth. And we're on a path to try and fix all the methane leaks, get them under control, but we do not have a global platform and real-time platform to do that. That's what Scepter set forth to solve in collaboration with AWS. Chance is going to talk to a little bit more about that with us later. And then also with sponsorship from ExxonMobil, because they're our anchor customer on this platform and have provided the insight to do so and set forth and understanding methane and getting our platform going. So this is an example of what we can do when we talk about making the invisible visible. What you're seeing here is a methane plume. And normally you would not see that. But through advanced data analytics and monitoring, we're able to not only detect the plume, but quantify it. So we know how much is leaking. I think that's probably close to a 15 kg methane per hour plume. So it's somewhere in between small to medium sized. But what we do is we detect the plume, but we also geolocate. So we can do attribution to a facility. And the importance to that is we developed a 5-step process in collaboration with ExxonMobil to take that detection and go and embed it in the workflow so it can be fixed. So our process is to detect and then quantify. So we know how big it is, and that's what you're seeing there. And then we inform. So we take our data through the cloud and through the Amazon cloud in a highly secure environment, and we inform ExxonMobil. This can be into a command and control center that they have, or we can push it into the field directly into handheld and apps. And once we've informed them, then we share further data through the cloud to abate the leak. So we then fix the leak. ExxonMobil fixes the leak basically with all the information that we're providing. And then we're in a position to certify and to inform the regulator that the leak has been fixed if a regulator is involved. So that 5-step process, given that we've built the Fusion platform, allows us to not only detect, but to embed into workflow. And we're very proud of that accomplishment. And then under ExxonMobil's leadership and the umbrella that they've created, we're able to expand into adjacent industries like waste management and understand methane emissions coming from landfill and other areas. So how do we do it? Getting into the guts, it's really a 2-step process. First is really a big data process where we ingest thousands of sensors and monitoring the atmosphere and going up through vertical elevation. What you find is that all sensors are not created equal, and there's different things going on at each layer. So we've taken a multi-sensor, multi-domain approach to monitoring the air column. So we'll take in terrestrial sensors, aerial sensors, drones, information coming in from stratospheric platforms that we've innovated on, and satellites, satellites that are active today, maybe satellites that we launch in the future. But that step is a big data normalization step where we have to create a big data cube from disparate sensors. Again, AWS has been very, very instrumental in helping us achieve that. And once we have that data cube and it's normalized, we're then in a position to fuse. So depending on the product that our commercial customer wants, we'll fuse with relevant data sets. So when it comes to methane detection, we're fusing with hyperlocal wind. And that's why you saw that plume move around and squiggly. I think that was probably 7 knots of wind in the Permian when we did that. Right? And through that fusion process, which is advanced data analytics and probably some AI, we then develop a higher level product for sale on a recurring revenue basis. Well, let's talk a little bit more then about the sensors in the column. I'll give you a little bit more insight there. We're active today by using some free sensors. So while we're operational, the way we're doing that is to take advantage of government and NGO sensors that may have been deployed. Maybe they were deployed for weather reasons or science reasons, and somebody's been able to write an algorithm to now turn them into methane detection. Could be a shortwave infrared sensor, et cetera. We're able to take that free data today and do a little bit more advanced math and take that from satellites and terrestrial platforms and aggregate that onto our Fusion platform. So we're generating insight today from free. We actually have a big federated data catalog where we're ingesting these sensors today and writing data algorithms. And then we, depending on the use case, we may find that we need to augment that. And we augment that with our own sensors. And so we actually do fly hyperspectral. And we're flying it currently at the stratosphere. We put together a hyperspectral package, and we fly it at 60,000 feet. And we've flown it over the Permian now 6 times, and we can get down to very, very low detection levels, so 10 kg methane per hour. What you find with the free sensors is that they're limited in basically 3 domains, and that's why we fly our own sometimes. The limitations could be gaps of coverage. Maybe they're covering certain areas of the world, and it leaves gaps in other areas because our customers are multinational or global in nature and they want a complete picture. Or it could be the timing of the reads. So terrestrial sensors, for instance, are very good at reading maybe like every 15 minutes. But satellites will read in days. So maybe it's once every 3 days or once every week. And so you have this difference in the temporal dimension that has to be reconciled. And then there's a difference in detection threshold level. Some of the sensors for methane, the terrestrial ones could be at 1 kg methane per hour, and they can just detect, they can't quantify, or they do not do a good job quantifying, I should say. Whereas satellites are at 400 to 500 kg methane per hour, so they're only picking up super emitters. So we have to reconcile these 3 different dimensions and fill in the gaps mathematically and through analytics. And at a certain point, you say, let's go fly our own customized sensors and pull it all together. And we're now expanding our stratospheric platform detection into aerial monitoring and taking our platform and perfecting detecting and quantifying leaks for offshore oil platforms. And again, we're doing this in collaboration with ExxonMobil. What we find is that offshore is responsible for 20 to 30% of all fugitive methane leaks. And we really need to do a better job on understanding that. So that's where we're evolving and how we can operate today. So a little bit more on the platform. I think when it comes to our stratospheric platform, we were the first to put together a hyperspectral infrared sensor in shortwave infrared that could specifically focus on monitoring methane over regional areas. We perfected this platform to get started by providing regional data today and evolving to global. So in this use case, we took a heritage sensor that had been flown before on several missions. And we put it in a thermal environment, modified it. These were at 60,000 feet. It had flown on aircraft before. And we put it on a 3-axis gimbal because the balloons sort of move around. Even though you can steer them, you just change elevation and you can have the balloon dwell. The advantage to this platform is that it helps us uncover another characteristic of methane leaks that still needs to be sussed out a little bit, and that's intermittency. So leaks turn on and off, but if you have the ability to dwell, you can then pick up this modality and have a better assessment of your total leak profile. Aircraft, they fly over. If the leak's turned off when they fly over, you're going to miss it, right? So we've done a great job with this platform. It's really exciting. And another point where we've innovated here with AWS was on solving and wringing out latency in the system. So we went in knowing that we could do a good job on the data analytics. But what you find is you've got a sensor that's throwing off a lot of data, but we had limited comms to pull it down even though we were using Starlink. And we innovated then on edge compute and moving the data around in a low latency environment. And we didn't go in thinking we were able to do that, but we were able to push down leaks down to less than 10. We're doing plumes in less than 10 minutes. And the standard sort of protocol for doing this is to use a process called inversion modeling. And that's usually a 1 to 2 week process. So we've innovated there. And then on the satellite side, our constellation is designed, and we've learned a lot from our stratospheric campaigns and hope to learn a little bit more from our aerial campaigns. But we'll take a suite of sensors approach there. And it's really at the satellite side where we get our revisit time down to maybe taking a read 50 minutes any place on the planet. And what that opens up is more of a B2B to C market applications as opposed to just B2B, because you start touching the consumer. And that gets really, really interesting on use cases as well. So to share a little bit with you there, this is going beyond just methane detection. So let's look at beauty and cosmetics, for instance. Okay, if you had that a real-time global data acquisition going on, you could work with multinationals who have a multinational and global marketing footprint. And for beauty and cosmetics, there's an intersection with, for instance, melanoma. It gets back to health concerns. But there's empirical research and equations that if you knew, for instance, the amount of ground level ozone, the subspecies of particulate matter at 2.5, and you had weather. So in this case, we'd be interested in temperature and humidity. And if we had a proxy for the size of your skin pore. So for that, let's talk about L'Oreal. If you had their app and for instance, they knew that you're white, Latino, or Asian, that could give a proxy for the diameter of your skin pore, and we could create and run a melanoma index. And they could then in turn push to you that you've reached a critical threshold of pollution on your body, and that you should run down to the Walgreens and go buy their body wash to get the negative effects of air pollution out of your system and reset. And they have done a multi-$100 million product launch to combat the negative effects of air pollution. So this is an example of how global real-time data can actually help generate revenue. It just doesn't have to be used for monitoring and compliance. It could be used to generate revenue, lower cost, or improve strategic decision-making. Another example of real-time would be for the insurance industry on where they're moving for dynamic risk allocation and evaluation. So it's not necessarily a policy that you implemented in February and then a catastrophe happens in June. We're now having events of activity come up. So it's volcanic eruptions, windstorms, floods. The insurance industry is moving towards dynamic allocation and doing it, allocating capability to cover either during the event or just before the event. Our data sets in conjunction with weather data sets could help in this endeavor. So wrapping up a little bit here and then going a little bit more into our platform, we're very, very happy and pleased with our relationship with AWS. They've been a great partner here in building out the capabilities of the Fusion platform and other endeavors. We started off really because of the environment. The attributes of scalability and the ability to ingest thousands of sensors. We borrow from their IoT group. A lot of times an API has been written to ingest a sensor or half of the code is there, and it allows us to more quickly do that. And then the security. As I had mentioned before, in order to do, for instance, the methane use case, we had to share confidential databases back and forth with our customer. And AWS does a great job in engendering security and trust. So we're good there. And what has also evolved out of the relationship, again, was this capability to use AI and edge compute to wring out latency in our data flow. Low latency is now, at least on the new space side, has become sort of the preeminent attribute surpassing low detection and accuracy thresholds. People want low latency. They want the answer now and more quickly, and let's say make up for the precision maybe through enhanced AI or other measures. And so we're really, really pleased that we've worked through that attribute. And we're also pleased now that we're live with about 4 products that you can find us on Marketplace. And so, please look for us there. And we look forward to moving quickly together over the next months to basically build the largest database of atmospheric information on the globe. So with that, I'll turn it over to Chance.
All right, thank you so much, Philip. I am going to continue and take us into part 2 of 3 in today's discussion. I'm Chance. I'm with AWS Professional Services, and we are the team of engineers that deploys out with Philip's team, like in Scepter itself, to be able to accelerate and enhance their mission to observe the atmosphere. So what I'm going to talk about today is very specific. We're going to look just at that methane use case, and we're going to teach some lessons learned from the last couple years of work and give you an idea of what it is we're up to and a little bit of a motivation as why we're pursuing it, and then how we're getting to the kinds of metrics that you heard Philip describe. So to begin, let's go all the way down to the ground. You have to imagine the little pictogram here is, say, some holding tanks, a waypoint for natural gas out in West Texas or East New Mexico. It's a set of tanks and then many, many millions of miles of pipes between these many, many thousands of tanks that are out there under harsh conditions. And you can, of course, have degradation to that equipment and then spring a leak. And these leaks, when they occur in the thousands or millions across many years, can contribute to the amount of methane in the atmosphere and set us up for difficulties in atmospheric health. So that's sort of the microscopic atomic approach where we look at an individual phenomena that is occurring, and we will dig down piece by piece through the platform to give you a sense of how it is we are approaching that atomic phenomena that is the methane leak out in the field. If we step back just quickly to motivate, we can very clearly see methane climbing at an alarming rate in its concentration in the global atmosphere. This is a little diagram from NOAA. Methane was not always as high as it is today. We're creeping dangerously close to 2,000 parts per billion on a global scale. This is just the last 40 years, and we've already traversed over 400 parts per billion. And this number sat 2 or 3 times lower for many, many, many years before the Industrial Revolution. So we have a very clear impact on this phenomena. And if we can arrest the release of methane to a certain degree, we can also have a very quick impact. You might hear a little bit more about it later, but methane has a shorter half-life in the atmosphere and is a more severe warmer. It absorbs infrared, which is wonderful for our detection because that helps us determine where it is, and it helps us quantify it using its fingerprint in the infrared spectrum. However, just like some fried chicken under the infrared lamp, it picks up heat very nicely. And so it will rapidly and aggressively warm the atmosphere in a per pound in a way that is more warming than CO2 even. So we have a huge opportunity here to potentially, in a cost-neutral manner, make an impact on the warming and the health of the atmosphere well within our lifetimes. Like CH4 is about a 10-year degradation cycle in the atmosphere, so we could actually see something very dramatic if we take action on this particular use case. So let's talk about the software and the hardware that's making it happen. This is a diagram that steps all the way back to the most abstracted view and gives you a simplified understanding of what it is we're up to. We've got the inputs and the outputs in red on the left and right. So environmental stimuli and things we're able to sense are on the left. And then the outputs, whether they are the analytics or the insights or actual suggestions for mitigating actions that we can take, are coming out on the right. In between, you've got the 3 green pillars. Those will recur throughout the presentation. You'll also see some titles that reference the ingestion phase, the processing phase, and the serving phase. Again, that is also a simplification, but that's principally what we want to cover in terms of what is this architecture and how does it function. To get us started, I want to begin at the foundations. And this is sort of the foundation for both Scepter's particular use case, but also for many builds. And so if you're starting out or you're looking to revise your architecture to make it more advantageous, take advantage of cloud principles, you might want to take a close look at this slide where we indicate both the method we used, which is the landing zone accelerator, which has a lot of literature available online. That gave us the guiding principles to set up a robust and secure environment in which Scepter operates. So you'll see that an example of that is here in the bottom in the green, our multi-account architecture, where we have specific separation of duties and in order to provide us with that clear, logical separation to aid in our security posture. So you'll have a management account for managing your identities, an account for logs for audits, and then we're just showing one app account here, but we have many accounts for different phases of the CI/CD pipeline. And then up top, I'm calling out some of the critical services that help us to meet the regulations and requirements and performance that we want to from the ground up. So for monitoring, we're looking at conformance packs and control tower and config and firewalls. In the middle, you're looking at logging both at the app level with CloudWatch and at the AWS service level with CloudTrail. And on the far right, you've got the key management service, which lets us handle and easily implement our encryption at rest and in transit. If we step a level deeper into how it is that we build, this diagram gives you a sense at the top from the developer perspective and sort of working down layer by layer into the app perspective. Again, it is simplified, but it gives you hopefully a sense for how it is we're building on the fly with many developers working sort of scientific elements, engineering elements, serving elements that are getting this platform out into the world. So you'll see here at the top, we've got developer environments, oftentimes leveraging QDeveloper for code speed and accuracy. We've got a number of branches that might be mapped to a feature or a portion of a feature. Those can all then feed into a central repository or a number of repositories that could be mapped across the application. And then if you get down to that third layer, we're looking at the logical components that make up the application. We're using CDK and CloudFormation in order to create that logical separation and make sure that we can deploy those applications in using infrastructure as code. And so those stacks can map one-to-one or many-to-one, as you see there, in order to deploy and maintain configuration for the application itself, which again is reflected in that same color scheme at the bottom through the ingestion, processing, and serving phases. Okay, let's dig in now to that first pillar, the ingestion. And we'll start to step into the use case itself again and talk not just about the software architecture, but start to introduce a little bit of hardware. So the example here is what is it we are bringing in? And you saw a hint of that earlier from Philip. I just want to review across all of those again in this diagram what exactly is coming into us and how we're able to organize those and begin the analytics. On the left here, we've got our principal sources currently. So we have a number of satellites that are operated oftentimes by governments or agencies like NASA and ESA. Those are powered partially through the AWS Registry of Open Data, which allows us to gain quick access to that data. In the middle, you'll see there are fewer arrows, but they're larger because we have sort of less frequent information coming in, but it is a very large volume. That's from our HAPS missions, or the High Altitude Pseudo Satellite. That is our stratospheric balloon, and it has that payload, the camera, that sits below the balloon. And we'll talk a little bit more about how exactly that works, but that is a vast swath of proprietary data that's really differentiating for Scepter, and which is, again, one of the many data sets we're pulling in. At the bottom, you see many small arrows, which are indicative of hundreds or thousands of IoT sensors that effectively sniff the atmosphere. They do this from an elevation on these poles that sit out in methane-producing regions, so out in oil and gas fields. And while they are very frequent, as Philip indicated, they cover only a very specific area. And so we can get the kind of wider coverage from our satellites and our HAPS vehicles, but we can have these wider networks of IoT sensors giving us very specific and frequent information about the production sites using those ground sensors. All of those flow into the right, into that first green pillar, which is ingestion. If we jump forward, I do want to bring up the hardware because, again, it is a key differentiator when we get to that proprietary data. And for a little excitement, I've got stratosphere in here, I've got space in here, and then cloud only made it into the red box in the lower right. But it should give you an idea from this schematic what it is we are doing when we're flying these proprietary missions. So on the left is HAPS. For the sake of latency, we were able to install a Starlink terminal on the HAPS vehicle. So instead of building up your images and then waiting and having one large slow downlink at the end of the day, or waiting even until the end of the mission and just getting a hard drive back at the end, we can pass data live through the Starlink nodes and then back to their ground terminals and straight into the internet and to AWS. And that is how we get to the minute level latency that Philip introduced. In this particular case, the link, while it's impressive, is not large enough to pull all of our hyperspectral data off of hundreds of spectral bands simultaneously down through Starlink to the internet. And so we needed to create some sort of onboard logic, onboard the balloon itself, in order to tighten the amount of data, right? So both to reduce and to compress what was in that signal, and then get it back in a way that still allows us to quickly discover methane and get those alerts to users. So to do that, we went and worked with the HAPS vehicle operator and created a containerized system that was handling the raw data that streamed off of the sensor and did some manipulations to it to remove unnecessary segments and to apply processing and then to ship that off to the Starlink connection. So in doing that, you could take data that might take tens of minutes to downlink as a full file and get something that fits within a 2-minute window, which is critical because our sensor takes data in these 2-minute chunks. And so if I fall behind on my 2-minute cadence, I will start to build up data and either have to throw some out or delay its delivery until the end of the day, or I will start to build up a backlog and I will not be able to do real-time detection on that minute-by-minute scale that we're aiming for. So to do that, we brought the total data volume delivered way down, and this slide indicates that. On the left, we have the timeline, and the bottom left on that duration schematic that starts with the vehicle and works its way to AWS. That's the downlink that we've been talking about here. That is hitting that 2-minute cadence on a regular basis, oftentimes less, and allowing us to keep up with the data production while having enough data fidelity to very accurately and sensitively detect methane out in the field. On the right side of this diagram, we have the AWS to user interface flow, which is well under 3 minutes in terms of processing and delivery to the user. And all in all, that makes us a 5-minute or less alerting system. And from the moment we might capture a methane leak with the camera until it actually gets to an alert on a phone or an interpretable image in the user interface. And that is ultimately the kind of latency that's going to allow us to address in large scale the many leaks that are contributing to methane accumulation. To go just a bit deeper, I wanted to talk about the middle green pillar, the processing, and give you a sense of how this data is used. In this diagram, you have in the upper left the vehicle, again, with its sensor. And I can say the sensor is somewhat like the camera in your phone. It does have an X and Y axis, right? It takes a 2-dimensional frame periodically. However, we use those dimensions differently. We have a crosswise dimension that works just like in your phone. It takes pixels that represent spatial information, but we use the y-axis to represent spectra, right? And we want to see across this wedge of the infrared, how bright are we? And if we have a particular fingerprint, we can determine that that is methane. And by characterizing and quantifying that fingerprint, we can determine how much methane is between us and the light that's reflecting down from the ground. That is what allows us ultimately to create those kinds of heat maps that have high methane, low methane markers, as you saw in Philip's slides earlier, and that we can then quantify. So the example here shows one of those many slices that are produced by the sensor. There are those darkened areas, which in the middle are shown as peaks leaning off to the left. When you have that low transmittance, what we can then do are take the algorithms and proceed to the green curve on the right to determine something like moles per square meter, which is a concentration measure, or even work our way using some of the wind data to get to kilograms per hour. So a rather specific and actionable data set that gives us the ability to hand that off to an operator in the field to prioritize and then potentially mitigate that release. Just to make sure you've seen the whole cycle, when we do get one of these, this is what the partially processed data looks like. You have on screen in purple the areas of absorption by the methane. And this is up in the infrared with false color applied. And you'll see that the wind with the green arrow is pointing off to the right. And so if we interpret the plume we see there, you have what is likely a source with the darkest, highest concentration of methane on the left, sort of swirling with a turbulent layer near the ground off to the right through the wind. And so that is what that looks like, and we're ultimately able to pick that out and then do those kinds of kilograms per hour determination on that data. All right, so we've worked our way through from stratosphere to space to the ground. We figured out what's present if there is a methane leak present, but we need to do a few more steps in order to make that actionable. So in the following slides, I want to cover that, give you an idea of where that's, how that is put together, and then we can continue with phase 3 of the presentation. So if you look here on this particular diagram, this is how we are cataloging plumes and raw data and data from other sensors as it comes into our system. So we have at the heart of our catalog the STAC spec, or spatiotemporal asset catalog. It is a specification which is becoming the convergent solution for organizing geospatial data and making it accessible to a vast swath of users around the globe. That database rides on Postgres, on Aurora, and it is loaded ultimately and then served out both through ephemeral endpoints using Lambda and then out via API gateway. Inside that database itself are a series of specification-defined logical hierarchies, starting with collections, which can represent, say, a mission or a particular sensor, and then items, many thousands of items that can sit inside of any particular collection. So we go from catalog to collection to items. And all of those have a very specific set of spatial information, and then a configurable set of metadata to make sure that we can provide information to our end users on the severity of the leak and how exactly to respond. So all of that, the processing pillar that we've talked about, right, the middle green pillar, rides on a lot of foundational services. So we certainly are using Lambda for sort of simple, massive parallelization. The STAC database, as indicated, is on Aurora. So we have an opportunity to use a managed and optimized Postgres instance. And then there are many open source libraries that are also helping us to speed up development and maximize the value per cost of the system, preserving a very large developer base for Scepter in the future, and creating an ease of interoperability for this system across customers of Scepter and other contributors to the project. I'm going to hop now to that final pillar, the green pillar that was serving, because once we've got this data, our alerts, we've organized it and indexed it in the catalog, we need to get it out to folks. And I unfortunately won't do full justice to this phase because it is very complex and has been hard won over a couple of years. But I will at least give you an introduction to how this distillation of complex information in a real-time environment is done currently and where we're looking to move with that serving system. So there's 3 types of serving of data illustrated on this slide. First is a hands-off method, right? SNS. We can ship an alert out as soon as we see something that looks like a plume with a certain degree of confidence, send that off to a team. And we can send it to Scepter for review and quality assurance, or we can send it directly to, say, an Exxon team out in Western Texas who can go inspect and mitigate the leak. If we step up in terms of complexity and interactivity, we have down below the other methods of serving, both APIs that gives programmatic access for mass ingest of the data or the discoveries, and also allows our end users like Exxon to continue to leverage their existing investments. There may well be very large and expensive GIS systems or just very sensitive algorithms or data sets that need to be fused. So the APIs give us a chance to interact programmatically at scale and gives the end user privacy in their interactions with the system. And then finally, we have the user interface, which is an active website used by Exxon and available currently, which has a number of open source components marked in red. So from the Cloudscape design system that came out of AWS to MapLibre and React to design the website. And we also have a number of services from AWS that assist us in creating a secure, scalable application like Location Service and CloudFront and Cognito. To give you a visual representation of that, the components that support the user interface are on the left. So you can see sort of CloudFront up front and React and MapLibre giving us a structured application. Then down below, Location Service and other systems giving us a foundation to operate from, including the maps that you see there. And then on the right, we have the application itself in a screenshot form with data posted on the left, those blue circles being locations of those IoT sensors that are out sniffing for methane. We have also foundational data visible with the yellow lines that indicate pipelines and likely places where a satellite might detect an incident or a leak that has occurred. And then finally, the standard features of an interface you'd expect that allow you to spatially and temporally query and explore the data on the map. The idea here, digging all the way from SNS to API to user interface, is that we are distilling the data and making it usable and valuable to the widest possible set of individuals. So that could be a data scientist or someone at Exxon who is studying this problem or beyond, or it could be an operator in the field who needs a very quick, intuitive sense of what looks the worst this morning and where should I go. All right, I do want to close just briefly by talking about where we go with this momentum. We have a lot of momentum. I want to cover trajectory. And so these bullets just give a very quick look at that. Of course, we are inspecting LLM opportunities through Bedrock to see whether we can make the user experience either easier, more reliable, or potentially transform that experience and give geospatial functionality to those kinds of features so that users can do more and more quickly than they could otherwise achieve. More importantly for the near term is SageMaker. And we're looking right now, as Philip mentioned, to drive our sensitivity down to the lowest possible amount, whether it's our data or the data that we are getting from these public sources. In order to do that, we're becoming pretty sizable users of SageMaker in order to make custom computer vision models, which are searching ever deeper and more accurately for these methane plumes in our data and the data of others. Finally, there's a huge job in moving to the satellite constellation. You heard the update from Philip that is underway. We have a sizable code base that will serve that well, but there's work to be done to get ready to someday manage those satellites and optimize their collection schemes and respond in real time, potentially altering the collection plan when we discover that there is a leak or an incident happening somewhere on the globe. So you put all that together, the increase in scope and scale, the increase in automation and accuracy and sensitivity, and we make progress towards what is ultimately going to be a more frequent and accurate system for monitoring and ensuring atmospheric health. And so to drill down one final time, it brings us back to this schematic scenario here where we have that methane leak. ScepterAir as a platform is able to automatically detect this on the fly from one of many sensors or a combination of sensors, derive a high confidence alert, and get that to someone who either in person or remotely can get to this leak and mitigate it in a timely manner. And with that, we are able to potentially have an impact on the future of atmospheric health. And we will now hear from Emily Reedy of ExxonMobil.
Okay. Thank you. So I get the last chapter in our little story, some perspectives from an end user. So as Chance mentioned, my name is Emily Reedy. I'm a member of the methane emissions research team at ExxonMobil, where we are hyper-focused on methane and developing technologies to better detect, quantify, and mitigate methane emissions from oil and gas operations. So since at ExxonMobil, what we kind of try to focus on is what we've known as the and equation. So how do we continue to supply the world's energy and do so while reducing emissions? So this graph here is showing overall emissions relative to 2016 when the Paris Agreement was signed. So we can see that since that agreement, ExxonMobil has actually significantly reduced our Scope 1 and Scope 2 emissions, and we have plans to do a lot more. So we have a 2050 net zero ambition across all of our operated assets, And our roadmap to get there is actually in place in several oil and gas basins right now, particularly the Permian Basin in West Texas and New Mexico, where our target, instead of being 2050, is actually 2030. And while this incorporates all greenhouse gases, a large portion of that revolves around managing methane. So as has been hinted at before, methane has significant challenges. This top graph right here is showing aerial surveys across 2 oil and gas basins. And I know it's a little bit hard to see, but each detection is being shown as where they are in terms of the emission rate. So it goes all the way from, on the lowest end, 10 kilograms an hour, which was the detection limit of this sensor, all the way up to thousands of kilograms an hour with some rare large emission events. So we need to adequately be able to measure throughout this entire range. And if you have a question of which sensor works best, the answer is all of them, all the time. So we are using a combination of sensors. We have satellites that give you large geographic coverage about once every couple of days, but at a higher detection limit in order to catch those large, rare emission events. Closer to the steeper part of the curve, we're using aerial surveys through aircraft and the high-altitude pseudo-satellites that can measure between 10 and 20 kilograms an hour. And then once we get even more localized beyond the region of this graph to the 1 to 10 kilograms an hour, that's where we're using site-level sensors like continuous monitors, as well as drones that can survey throughout an entire site. We can even go lower with the equipment monitor, with individual equipment with a handheld camera. But one of the challenges with using all these different types of data is that they all produce different types of data at different frequencies. So we need to have a data fusion platform that can deal with all these disparate data types and different times that you're getting them. So as has been mentioned, continuous monitors will give you data every 15 minutes or so. Satellites will give you every few days. And aerial surveys will give you a ton of data, but maybe only a few times a year. We also need to be able to process data quickly and accurately. As Philip quickly mentioned, that these emission events can actually be intermittent, so they can start and stop on their own, or be tied to a particular process, so you only notice that there's a problem while a certain process is going on. So if we don't find out very quickly that something's going on, we could be sending our operations to go check on an emission event, and then the emission event would have stopped on its own. So we don't want to be sending our folks in the field off to go chase ghosts. So we want to make sure that we're using their time efficiently and actually sending them to regions where we might be able to accurately fix any of the problems. A data fusion platform will also need to scale globally. So ExxonMobil operates in 6 different continents, and that's going to produce a lot of different data. With methane emissions monitoring, so we need to be able to actively scale from our test basins right now to a much more global monitoring. This also needs to be flexible and fit for purpose. Methane is in a region of evolving regulatory landscape, and there's a general push to incorporate a lot more measurements into reporting. So as that's still getting figured out, we're going to need to be able to easily access any and all measurement data in order to comply with any reports. So our current emissions alerting workflow is that we're taking all these disparate data sets. So we have our satellites, our continuous monitors, our aerial surveys, and our drones and UAVs. And all of these observations are going to our Center of Operations for Methane Emissions Tracking, or COMET. So our operators in COMET are taking all of these observation data and pairing it with our internal monitoring process data. So this is going to be things like our tank pressures and flow values and things like that. So they're using all of that in order to get an idea of what's going on so that they can alert the right field personnel and give them a good sense of this is where we think the emissions are occurring. But a data set like Scepter could kind of ease the operational burden on our folks in COMET, so that way every alert is the exact same alert with, they don't have to worry about incorporating different types of data that's coming in at different times. So if there's an alert, it's coming in the exact same way, and they can just focus on doing what they do best, which is pairing it with our internal data and alerting the right field folks with the information that they need in order to actually mitigate the emissions. So to kind of quickly summarize, our requirements for a data fusion platform, we need it to be flexible and be able to ingest disparate data types. It needs to be automated with fast processing in order to reduce the latency, in order to get field personnel to the right locations at the right times, and be able to securely scale up across global assets and produce clear, actionable alerts and notifications. So a data fusion platform like Scepter's, with our current monitoring and mitigation efforts, will help efficiently reduce our methane emissions, including several goals, like our net zero and operated assets by 2030. I think that's all that I have. We may have time for a few questions, but if not, I think all three of us will be hanging around outside if you want to come and approach us. So thank you.